How about you guys doing with the homework assignment? It's all good? Done already? It has been done for days? Something like that? Okay, that's what I like to hear. Is it done correctly though? Just because it is done. Okay. Okay. Okay, so what I'll do is I'm going to pass the roll sheet around first. Okay, just so that you guys put your name next to it. Go. So does that mean that I don't have does that mean we don't have to review the homework assignment that's due on Thursday? It's all good? Everything is okay? Yeah? Okay. All right. So what we'll do today is we'll just continue to talk about subroutines, and we just kind of stack up some additional concepts on top of what we have learned already, which is a lot. I was surprised that people do not have questions about all the concepts that we have learned, especially return values. Okay, return values can be a little bit confusing, and yet I have not seen anyone. Yep, go ahead.
It might be good if we did a little bit more on return
Okay,
values.
let's do that. Okay, so right now I think it's a good idea to take a look at the updated material on subroutines, which is basically a revamped version of the other notes. It's not incompatible, it's just a better way to get the same material presented. Yep.
Where do we go on Moodle again to access the revamped notes?
It's all under topic 8, and it's
okay.
updated material on subroutines. So basically, whatever link you see on Moodle, you should definitely click it and remember whether you have clicked it or not. Can you see whether you have clicked a link or not, not relying on the browser itself? Does it give you the ability to report, what you have already seen? No? No? Okay. I can look into that because I know Moodle can actually allow you to take a look at your own participation in terms of, what topics you have clicked already, what you have read already, and stuff like that. Okay.
I've got kind of
Yeah.
a question.
Go
I
ahead.
think that, or at least for me, I understand the material as we've been tracing it and stuff.
Mm-hmm.
But my concern is if we were actually writing code, I wouldn't really know when to use the return statement versus the by ref parameter.
Okay, that's a valid question. It's basically knowing how to use a tool, but may not know when to use that tool when you're building a house. Basically what we are doing today, or in this class, almost the entire semester, is to perfect the technique of how do you use a drill, how do you use a hammer, how do you use a tool. But you're asking, when I'm building a house, when do I know that I'm supposed to use, the air hammer? When am I supposed to use a nail gun? And when am I supposed to use nails and versus screws and stuff like that? That's a question that you will have to deal with in cisp360. Now, in this class, we kind of talk about those things, and you can look at the sample code. But designing an algorithm, is actually more of an art than it is a science. So it's really hard to kind of describe the concepts involved, when people actually write algorithms. You just have to do it a lot so that you get a feel for that. But it is also very important to get the tools down first. Okay, that's what we are doing in this class, is to make sure that we understand all the tools that are available, so that in the next class, which is cisp360, you won't have any problems with the tools. It's just a question of when to use what tool when you actually build a house. But that's a valid question, and I think it's almost impossible to teach how to design an algorithm. It's almost like writing an English paper. I can tell you the general approach, which is top down. You have to break your paper down into several sections. You need to have the introduction. You need to have the summary. You need to make your point and support your claims, and have paragraphs to connect to each other. We can describe the syntax. Okay, it's just like in English. Programming languages also have syntax that we call grammar. They have grammar that we call syntax. So all that stuff can be described, but when it comes to actually composing an essay, it's still kind of difficult to describe how it is done. Okay. But that's a good question. We'll keep that in mind, as we come up with more algorithms. Okay. So what we'll do today is introduce the concept of using arrays with subroutines. Okay, because up to this point, we have only used regular, single variables when we have parameters, local variables, and well, those are the only two things. So what we'll do today is, just to extend what we know so far about subroutines, so that we can also include arrays as a part of the whole thing. Sorry?
Oh dear.
But it's not any more difficult, because it's just because those concepts are orthogonal. They are perpendicular to each other. Yep.
Briefly review return values.
Okay, we can talk about return values. In fact, I can probably give you guys just a little bit more work on just return values first. Okay. So let me give you something that is really simple, and you guys will just laugh and go like, why are we doing this? 5val x, 5val y, and all add does is to return x plus y. Okay. Indentation. And I'll just have one more here. It's not really needed for this example, but I will just go ahead and define that too. So we have multiplication, 5val x, 5val y, return x times y. And define sub, just like that. And we'll have our main subroutine to print the value of an expression. So we'll say print, and then we'll invoke the multiplication. And let's just say that we want to multiply 5 and also the result of invoke add 4 to x and 6 to y, and then the whole thing to y, like that. Okay. So this is the subroutine, or this is the pseudocode that we'll trace first, because I think it gives you an idea of, the flexibility of how return values can be used when you use a subroutine. Before we trace it, we'll just kind of stare at it and just kind of understand in general what this program is trying to do. If you just look at add, which is from here to here, are there any questions about the definition of the subroutine add? It takes two parameters. One is called x and one is called y. They're both passed by value, which is the easier of the two. And all I'm returning is just x plus y. And then we have the other subroutine. The other subroutine is called multiplication, or molt. And it's almost exactly the same, except instead of returning the sum of x and y, it returns the product of x and y. Are we doing okay so far with this? Okay. So the subroutines are not really that difficult to understand. They really perform simple operations. But when we come to line 11, what exactly is it doing? Well, when you encounter nested parentheses in mathematics, what do? Do you evaluate the outermost stuff first, or do you evaluate the innermost stuff? The innermost stuff first. So in this case, we do exactly the same thing. You look at the nesting of the parentheses, and the first thing you want to do is to evaluate this part here. Okay, what do you think that's going to return? Just without even tracing it, what do you think that's going to return?
10.
It's going to return a value of 10. In other words, the highlighted portion that I have in the spreadsheet is nothing more than just 10 once it is evaluated. What are we using that value of 10 for?
Y.
To specify the parameter y. Parameter y of which subroutine? Of multiplication. Very good. So that means when we actually perform the multiplication operation, which is the second invocation, we will be multiplying 5 and 10, and that will give me a value of 50. This entire thing will evaluate to 50, and that's the value that we'll be printing. Okay? So it's nothing more than, if you want to look at it this way, this is nothing more than 5 times 4 times 6. 5 times 4 plus 6. There we go. Okay, that's what it's doing. It's just doing it in a very clumsy way. Okay. But why do I want to do things in such a clumsy way? Just because I can?
So you can change the numbers?
So that we can change the numbers. What about multiplication not being exactly just multiplication? So I can do the dot product of two vectors. Okay, instead of just adding two numbers, I can give it arrays, so I can actually use this same technique to perform calculations on, say, linear algebra stuff. Okay, because addition is not just addition. Addition can be defined for numbers that we know. It can also be defined for complex numbers. It can be defined for vectors as well as matrices. So as we add more and more concepts to programming, what we call add may not be a simple add that we see here. But the concept is still the same. If add is returning the sum of the two things, they can be matrices. And if multiplication is returning the product, which can be a dot product or a cross product of something, we can use this method to stack up the calculations. We can utilize the result of one calculation immediately, as one of the parameters of another calculation. Okay, so that's why it is significant. It's not really just for adding, plain numbers, which we call scalar, but it can also be applied to matrices, vectors, and other things that we can add and subtract and multiply. Okay. Now, since we're on this topic, let me just give you, the different ways of writing 5 times 4 plus 6. This is called the infix notation, which is what we have been trained to recognize and deal with since elementary school. Okay, it's called the infix notation because the operator to specify the operation is between the numbers that you want to operate on. Well, there's another way to express the same thing. It's called the prefix notation. In the prefix notation, we specify the operation first, and then we specify what we want it to operate on. So that will become something like this. Okay, because in the prefix notation, we first have to specify we want to perform a multiplication as the outermost operation. And then, multiplication requires two numbers. The first number we supply is a 5, and then the second number we want to supply is the sum of 4 and 6. This is called the prefix notation. But there's one more way. We got infix, we got prefix. What do you think is the next one? It's called the postfix notation. Now, the postfix notation is actually the most interesting one, because how do you do a postfix notation? Well, you supply the numbers first, and then you tell the computer what to do with those numbers. So I'll just give you an example here. You don't have to exactly understand what that means. So we will say 5, and then we specify 4, we specify 6. Then we say, oh, by the way, perform an addition to the last two numbers, and then that will turn into a single number, and then multiply, the result of that to 5. So this would be the postfix notation. Is 5, 4, 6 plus, because the plus applies to the 4 and 6. So these three things will evaluate to a single value, which is 10 in this case. So then it will become 5, 10, multiply, which is basically multiplying 5 and 10. That's called the postfix notation. And you can see that the postfix notation has one advantage over the other two. What is the advantage? It does not require parentheses. Okay, exactly. Okay. And you might think that the postfix notation is really weird, and who in the world will use a postfix notation for anything? I mean, that's just looking weird. Can anyone answer that question? I don't think we have anyone here old enough, besides myself, who have exposure to the reversed Polish notation method with a calculator. Who has an HP calculator? Okay. That's why you guys don't know what is reverse RPN, reverse Polish notation. The HP calculators, at least back in the 80s or even the 90s, do not have parentheses, and yet they are used for scientific purposes. Scientists use HP calculators to do all sorts of calculation, and yet it does not have parentheses. It doesn't have those keys, and this is how people do it. Engineers and scientists in the 90s, 80s, and before, will use reverse Polish notation to enter equations that we normally, see as the infix notation. And if they are good at it, they don't even need to write it out. They can look at an infix equation and then translate that into postfix notation in their head. Okay. What else? What else do you think would use the postfix notation other than crazy scientists and engineers? Has anyone heard of postscript? Okay. What is postscript? It's a language, but it's a language intended for what? What is the purpose?
Is it for printing?
It's intended for printing, exactly. Because what it does is it's basically a sequence of instructions sent to the printer and say, draw a dot here, draw a line from here to here, draw a circle over here, and draw a Bezier curve over here. And guess what? That particular language is also using the postfix notation, and hence the name postscript. Okay? Now postscript has a descendant that we all know. Can anyone name the descendant of postscript? All you have to do is to remember who created postscript. It's Adobe. So what do you think is the descendant of postscript?
PDF.
PDF, exactly. PDF is actually based on postscript for the most part. So PDF internally still has postfix notation to specify how to draw something on a piece of paper, or on the screen, or on a printer.
Is that why the text normally scales well? Because it's vectorized?
Exactly. Yep, that's exactly what it is. It's just that, in the good old days, postscript is usually sent directly to a printer. You can still capture and have a postscript viewer, so you can view a file that is intended to a printer, and you can see exactly how it would be displayed or printed on a piece of paper, which is exactly the purpose of PDF. Okay. So that's just a little bit of trivia, of infix, prefix, and postfix notations. All right, so looking at this one here, just look at this expression. Which one do you think it resembles? Does it resemble infix? Does it resemble prefix? Or does it resemble postfix notation? It's a prefix notation. It's just a whole lot more clumsy because we have to say invoke mult, to specify we want to multiply, and we say invoke add when we want to perform add. But other than that, it is really just a prefix notation. Because we specify the operation first, and then we specify what we want it to operate on. Okay, so that part is not too bad. And then what we'll do is we'll trace this algorithm. And this is how I would trace this one, because the last line is so long, I don't want it to be taking up too much of my desk space. So here is the way I usually do it, is to maximize the use of the screen, and so that the long line does not really take up too much space. All right, let's go ahead and trace this one. This will be a fun one to trace. Okay, we have line number, we have precondition. Do we have any global variables here? There are no global variables, which is great, okay? Because we don't want to use global variables if we don't have to. In this case, what is the first line that we should execute? Line 11. That's the only line that is outside of the definition of a subroutine. And okay, so here comes the mysterious part. What are we going to do with line 11? I think I probably need to kind of scroll it up a little bit because people in the back may not be able to see the whole thing. So I'll just kind of scroll it up like that. Okay, there we go. So what are we going to do on line 11? What is the last thing we want to do on line 11? Printing, right? Okay, we have the number, then we print it out. What is the second last thing we want to do on line 11? The multiplication. We cannot do the multiplication until we are done with the add. So that means the first thing we want to do is what? Is perform the add operation. Okay, this is the first part that we have to deal with first. So that means the first time we get to line 11, the first thing we want to do is to take care of this particular invocation. Okay, well, do we know how to invoke a subroutine? Yeah, we do. So what do? We have to specify a return something. In this case, it has to be a return info instead of a return line number, because I have to return back to line 11. except when I do get back to line 11, I have the next thing I want to do would be the multiplication, and then the next thing I want to do is the print. Okay, so that's why we have return info instead of return line number, because a return line number is not enough to tell me what else I have to do on that line. Okay, did someone come in late and not have a chance to? Okay, so I'll just pass it here. So the return info is going to read like this. Line 11, we still have the print not done yet. We still have the multiplication, invocation not done yet. So we'll copy almost the entire exact line, except the invocation we are taking care of right now is replaced by a single question mark. The question mark is essentially a placeholder. It is a place where the return statement can replace it with a particular value. And that's why we have a question mark. Are there any questions about this step here? Because this is the most important step of this example, is we only take care of one invocation at a time. And in this case, we pick the one that is the innermost, which makes sense. Any questions about this step? No questions? Okay. Then the next we want to do is to find out what parameters are we passing to add, because we are invoking add. Add requires two parameters. One is called x, one is called y. So let us go change the size of the columns a little bit so that we can see everything at the same time. Something like that. Okay. So what is x initial value? X initial value is 4, and y's initial value is 6. Okay, because we are invoking add at this point. Okay, so now we have return info set up. We have parameter x, we have parameter y all set up. It is time to go into the subroutine. The subroutine itself is easy, okay, because we are looking at subroutine add. Subroutine add only has one line that does anything really useful, which is line 4. Line 4 is saying, okay, let's go ahead and return the value of x and y. X has a value of 4, y has a value of 6, 4 plus 6 is 10. What are we doing with 10?
Repeating the question mark.
Replace the question mark with a value of 10, exactly. So the next thing we have, okay, I just erased it. The next thing we have to do is to copy and paste the return info cell entirely, and then just change the question mark to a 10, because that's what returning means. It is replacing the placeholder with a specific value. In this case, it is being replaced by a value of 10 because 4 plus 6 is 10. Are we doing okay so far with the execution of the return statement? After the return statement, we go to line 5, which is the end of the subroutine. And in this case, there are several things we have to do. Some of these, it's kind of confusing. The first part is to look up the return info cell and tell us, okay, where am I supposed to go back to? I'm supposed to go back to line 11. Now, when I do go back to line 11 now looks like the cell B5. It is no longer the same as in the original code because we have resolved the result of adding 6 and 4. Are we doing okay so far with that concept? Okay. The second thing we have to do at the end of a subroutine is to deallocate all the columns that we have allocated for this invocation. So that will be these particular, columns. And now we're back to line 11. What are we going to do next on line 11? Remember, line 11 now looks like this. Can I do the print at this point? No. What else do I have to do? We have to invoke the multiplication subroutine. Okay. So it's basically the same thing. In order to invoke multiplication, you have to set up return info because every time a subroutine returns a value, you have to use return info instead of return line number. You can look at return line number as a shortcut. Okay, it's just a easy way to express the same thing, except since it's the next line, it's you can just report the line number. Okay, what should we put here as return info when we invoke multiplication? Exactly. It becomes a whole lot easier because this time the subroutine we're invoking is multiplication, so that means the entire invocation of multiplication is replaced by a placeholder, which is the question mark. Okay? Multiplication also requires two parameters. One is x and one is y. What do we put in x? 5. And what do we put in y? 10. That's right. And now we are ready to go into the subroutine. If you look up multiplication, the only line that does anything useful is line 9. So we say line 9 here. And line 9 is returning x times y. Okay, let's find out what is x times y. X is 5, y is 10, x times y is 50. What we are going to do with 50 is just to use it to replace the question mark, which is the placeholder, like that, and we are done. Now remember, when you execute the return statement, all you do is to replace the question mark with an actual value. You do not execute that statement at this time. This is not the right time to execute a statement. All you're doing is to resolve the question mark so it is no longer unknown. Okay. And then on line 10, the first thing we do is to look up the return info cell. It tells us that we have to go back to line 11. But this time, when we get back to line 11 will look like B9. Okay, in other words, we know exactly what to print when we get back to line 11, but we're not there yet. The next thing we have to do on line 10 is to deallocate the 3 columns that we allocated for that invocation. And then on line 11, we actually do need a comments column here because we are printing something. Because we are printing the value 50, so we'll just say print 50, and after that we're done. Are there any questions about this trace? Now this trace is somewhat tricky because when you look at the program, when you look at line 11, it seems like we have a invocation stacked up on another invocation, because it seems like we should be allocating a little bit more than 3 columns, okay, maybe 6 columns. But that's not true, okay? As it turns out, when we execute line 11, all we have to do is to evaluate or invoke the subroutines one by one. We evaluate add first. When it comes back, then we evaluate multiplication. So we don't really have to stack up. It's not a case of recursion or nested subroutine call at all. Are we doing okay so far with this example? In terms of the concepts and also the mechanics of how everything is done. Is that okay? No questions? All right. Yep.
So the return info helps us to clean up our algorithms and make them smaller and more compact.
It helps us track down what else do we have to do when we get back on a particular line. Because when you look at line 11 here, it is fairly complicated. There are a lot of things, but I cannot do everything at once because I don't know what I should specify to y unless I know what the result of add is, right? So that's what return info is for us to keep track of what am I doing at this point and what value am I resolving so I can continue the operation on that same line. Yep.
So, if you're invoking a subroutine, like if it's one line in the global sense of the program and it invokes 2 subroutines, will it always use the same column and deallocate the first one, or will there ever be an instance where
it is stacked?
Yeah.
No, they would never be stacked, if it is arranged like this. Because because you cannot evaluate, the multiplication in this case until the add is done. So there's no need to do the invocation of multiplication unless the add is done. But when the add is done, then those columns are freed up so you can reuse the same columns. Okay. So this is a really kind of important concept, because you have to remember the order of evaluation, and that determines what goes first. But the most important part is you only need 3 columns in this case to deal with this particular expression. Any other questions about this one? So are we still doing okay with in terms of subroutines, returning values, and stuff like that? Okay. Let me save this file first, and then we'll move on and talk about how you can use arrays in subroutines as parameters and also as local variables. Let's call this one add default. And now we'll go ahead and did I talk about how we can use recursion to deal with binary search? We did, right? So what we'll do is we will do exactly that. So we say define sub binary search, bsearch. It will take quite a few parameters, so I cannot make this example really long because otherwise it will take up so many columns. It's not going to be very clear what it does. Okay, so we'll say by rev a, which is an array, by value b, by value e, which is the index of the last element in a that can still contain the value k. So then we have by val k, which is the value that we are looking for. Okay. Okay. At least does this part look familiar? We have the array. We have the index of the first element. We have the index of the last element in the array that can still contain the value k. That's basically the same notation that we used in the other algorithm. But this time, they are no longer just variables. This time, they are parameters. They are passed by the previous invocation. And then we have a local variable for m, which is the index of the quote-unquote current, is the index of the current element that we are looking at. Okay. So this time, let's see how we can specify the logic of binary search. First of all, which element okay, how do I end binary search in the other algorithm? We stop when, but there are two ways to stop the algorithm. One way is when, what is the special relationship between B and E that tells us, oh, it's time to stop because the element is not there?
When B is greater than E.
When B is greater than E, exactly. Because B starts from the very beginning and E starts at the very end. They get closer to each other after every comparison, but when they overlap, when B crosses over to become larger than E, then we know the element does not exist in the array. Do you still remember that part? Okay. So we can do that. Okay. Now don't ask how this becomes the case. It's just that somebody asked me to search for something in the array A, and somebody tells me that I should start with index B and end with index E, and K is the value that I'm searching for. So as far as I'm concerned, I don't really care why B is greater than E. I just know that if B is greater than E, then there's no need to search anymore because the element is not there. Is that making any sense? Is this part making any sense? Does it match the algorithm that we have talked about in a non-recursive way? Okay, it captures the same logic. It's just that it's no longer a loop. Okay, well, let's take a look at the second case. Okay, else. Now the else basically means B is not greater than E, which basically means B is less than or equal to E. In that case, we better look into the array and see whether we can find the one thing that we are looking for. So in this case, we have to compute the index m, because m is the index of the quote-unquote middle element between B and E. We already know how to do this calculation. It is the floor of B plus E, the whole thing divided by 2. Are we still doing okay at this point? Do you guys still remember that m is the index that is of the element between the B and the E? Yep.
What's the floor again?
Floor is kind of rounding down for the purpose of this program. It is equivalent to rounding down.
Pierce integer.
Like 2.5 is rounded to 2. 2 itself is rounded to 2 as well. 3.5 is rounded to 3, and so on. So it's basically just a way so that in case B plus E becomes an odd number, because if you divide the odd number by 2, you end up with a fractional part. We're just tossing the fractional part away. And once we have m as an index, of an element, the next thing we can do is to do the comparisons. Okay. So in this case, I change the algorithm just a little bit and say if a bracket m equals to k, which is the easy case, what do we do in that case? Well, logically, what does it mean? Return true, because we have just found the value k in the array. Very good. So we just say return true. That's easy. That. What if a bracket m is less than k? Assuming the array is sorted in a non-decreasing order, so kind of like increasing but not exactly. Okay. So in this case, which half should I toss away? K is already larger than a bracket m, which means it's going to be larger than a bracket m minus 1, m minus 2, m minus 3, and so on. So we are tossing away the left-hand side, or whatever is to the left-hand side of a bracket m, including a bracket m itself. So what should I do here?
K becomes B.
K becomes B.
B becomes E.
No, B becomes m plus 1. Okay, we are changing the index of the first element to become m plus 1. Okay, but that's the old way of doing things. This way, when we use recursion, we'll just say that, well, I don't know whether we have an element with the value k, but I know who to ask, because I know that bsearch will know the answer. I will give bsearch the same array that was given to me to search but instead of b as the index of the first element, I'll tell bsearch, oh, don't even bother with anything before or including m, because I know that that's not going to be containing the element with the value k. So you can start with the index m plus 1 instead as your beginning index. E is still the same because I haven't done anything with the end, and k is still the same as k because that's the same value that we are looking for. Okay, let's kind of stop here. Instead of tracing the algorithm, we just want to take a look at this and see if it makes any sense. Okay. Now, when you look at this, you just have to look at it, not in the sense that, but tag, we cannot do it because bsearch is not done yet. We are not done defining bsearch, so this is not possible. Keep in mind what bsearch is supposed to do. Okay, what is bsearch supposed to do? It is supposed to take an array, which we call A, and it takes an index of the first element, the index of the last element in the array that can still contain the value k, and we want to confirm whether k is there or not. That's the job of bsearch. So in here on line 14, if I already know, if I had just confirmed that a bracket m is less than k, I know that the first element that can have the value k, is a bracket m plus 1. I know that part already because I'm the one who did this comparison. But instead of having me to search through the other part of the array, I'm just passing it on to the next person. It just turns out that the next person is running the same algorithm that I am running, except the next person has a smaller portion of the array to search in, because now that person can start with the index m plus 1 as the beginning index instead of my beginning index b. Is that okay? I mean, yep.
I don't remember the original exactly, so m is the element we're looking for, or?
Okay, m is the index of the element that we are staring at in the array.
So it's the placeholder, but it's not what we're actually looking for.
It's not a placeholder. Let me just give you an example. Okay. Okay, so we have indexes on one hand, 0, 1, 2, 3, 4, 5, 6. Okay. And then we have the values, So since we want it to be sorted, we have to make sure that it is sorted in a non-decreasing way, which basically means I can have 2 3s in the array, because duplicate values are allowed. Okay. So in this case, what do you think is the first element that I want to compare to? So let's just say that we are looking for k equals 4. Okay. What is the first element that I'm going to compare to?
0.
In the middle, right? So we want to compare to this 3 here. So we have to say 3 is less than 4, right? I'm looking for the value 4. And the array has the values -1, 0, 3, 3, 6, 10, and 20. I start from the middle. Binary search starts comparing from the middle. So if I already know that the value that I'm looking for, which is 4, is already greater than the value in the middle of this range, the entire range, what is that telling me?
It's also ranging 0, 1, 3.
Exactly. It tells me that this entire portion of the array cannot possibly contain the value 4 because the array is sorted, right?
Yeah.
So this is M. M is controlling which element in the array we are comparing to. That's basically the role of M in the entire thing. Is that okay?
Yeah, I just forgot what.
Okay.
what's
I think in the
possible.
original algorithm I changed the notation to I, not M. So that's why that might be causing the confusion. But since we have this example here, we'll go ahead and just finish this one, just so that people have another reference at this point. So this portion of the array is already confirmed that cannot have the value 4. I only have 3 values left, or 3 elements left in the array. Of the 3, this one is the middle. Okay, the one with the index 5 is in the middle. So this is what I will compare next. 10 turns out to be greater than 4. Now, if 10 is greater than 4, I already know whatever is to the right-hand side of 10 will also be greater than 4 because the array is sorted. So that means these two numbers cannot possibly have the value of 4, and as a result, I will eliminate those as having the potential of having the element that I'm looking for. So now I only have one element left, which is 6. 6 is still greater than 4. Which tells me that I can eliminate everything from 6 all the way to the other end of the array. At this point, I have nothing left in the array that can still have the value 4. That's the general approach of binary search. So switching back to our example here, I'm just telling the next person what part of the array may potentially contain the value k. It's just that person is holding a piece of paper which is the instruction that is the same as my instruction, but the numbers are different. Okay, well we'll go ahead and finish this definition, and then we'll trace it with a very, very short array because obviously with a longer array this is going to be quite painful. Okay, so the last one is what? Invoke bsearch. My array is still passed on just fine, but this time b is passed to b, m-1 is passed to e, and then we have k passed to k. I think I'm missing one parameter. Which one am I missing? Nope, I'm not missing anything. It's just the indentation is wrong, because otherwise they should line up. Okay, we have n if here. And if here, and define sub. That's my subroutine. Okay. So the main program will just say, invoke bsearch. I have to specify the array. So let's just call our array, b. Okay. So b is specifying, a as a parameter. Since this is the beginning of the entire search, b has to start with 0 because 0 is the first index of the first element of the entire array. Bar b bar -1 specifies e because that's the index of the last element in the entire array, and we'll look for a particular value. Let's look for 5. 5 specifies the value that we're looking for, which is k. I have to give you an initialized array for this to work, because otherwise I give you an unknown array. There's no way you can search in an unknown array. So are we doing okay in terms of the code of the algorithm, or do you guys want to spend some more time on the algorithm itself? Let me just maximize the screen so we can see the entire thing. There we go.
Why is B also the value of A?
Where are you looking at?
Because the by reference for in the print.
Oh, that's a different B. I should use a different symbol. I have to give you an initialized array to begin with, so we'll just call that C. C is the name of the global variable array that is already initialized, because otherwise there's no way you can run this algorithm. Okay. Let's go ahead and trace it, because this is going to be somewhat interesting to trace, and it illustrates a lot of stuff that we can do with subroutines.
So it should be, it should be bracket C, bracket -1, right?
No, that is not the case. Because we have to pass the entire array in. Let me show you what sheet 2 looks like. Okay, sheet 2, which is what we use for the tracing, will have comments, it will have line number, and the array C. Let's just say the array C has 3 elements, because we don't want to make this exceedingly difficult. So C has 3 elements: C bracket 0, C bracket 1, and C bracket 2. That's my entire array C. It only has 3 elements. And I have to give you specific values, because otherwise there's no way you can compare elements in the array C. So we'll just say it is 2, 6, and 10. Okay. That's the precondition. This is the precondition of the entire algorithm. I have to give you the exact value, give you how big array C is and what are the values in array C. Are we doing okay so far with the precondition? Are we ready to go in and actually track down what the algorithm is going to do? Okay. So the only line that is outside of the definition of the subroutine, and in this case we have a fairly long subroutine, is line 20. Line 20 wants to invoke, we want to do some printing later on, but before we can do the printing, we have to know what we are supposed to print. Are we going to print true, or are we supposed to print false? So that means we have to invoke the binary search algorithm. And in order to do that, we have to specify one column for return info, because I have to remember what else I have to do when we get back to line 20. Are we doing okay so far? Yes? Okay, we're not lost or anything? Okay. All right, so we have to get back to line 20, but when we get back, all we have to do is to print out whatever this subroutine invocation is returning. And that's why it is just replaced by a single question mark here. Now here comes the kind of more difficult part. How are we going to specify parameter A? Because when we invoke B search, we have to specify A, B, E, K, and we have our local variable M. That's the easy one. Every local variable starts with an unknown value, so that's the easy one. K is easy too, because it is just 5. E is easy because it is, oh, okay, I made a mistake here. It's bar C bar minus 1, and since C has 3 elements, bar C bar is 3, 3 minus 1 is 2. B starts with a value of 0, that's easy too. A is the difficult one. How are we going to express that A is the reference to an array, not a single value, but an array? Well, in this case, we'll just say it is also known as column C to column E. We give it a range of columns to refer to. Are we doing okay so far? Because before, when you pass something by reference, it is just an alias of a single column. Now that we are passing an entire array by reference, the parameter becomes a reference to a range of columns. It's not just one, but a bunch. Are we doing okay so far with this concept? It's just an extension to what we already know about passing by reference, because now we are not referring to a single column anymore, we are referring to multiple columns. Okay, shall we move on? Okay. And this is going to be a little bit hard to track because I cannot display enough lines or enough space of this spreadsheet. So the best I can do is something like this. So now we're going to the subroutine starting on line 7. Line 7 is easy because all it does is to compare B and E, and the answer is no, it is false. Because B has a value of 0, E has a value of 2, B is greater than E is false. That means we have to go to line 10. Line 10 wants to compute B plus E divided by 2. B is 0, E is 2, B plus E is 2, 2 divided by 2 is 1, and the floor of 1 is just 1. That's why M, okay, this makes it a little bit hard, doesn't it? M becomes 1. Then we move on to line 11. Line 11 wants to compare A bracket M to K. A bracket M equals K is what? Well, first of all, what is A again? A is also known as column C to column E. Okay, because this is what we need to look at A. A is column C to column E. Well, it is an array. With any array, we can do indexing. M has a value of 1. It is on the other side. We cannot see it right now. But it has a value of 1. So we are looking at A bracket M here. This whole thing is referring to A bracket 1. But since array A is the same as array C, starting with column C, we are looking at column D at this point. Column D equals K, which is 5, is false. Are we doing okay so far with this comparison? Maybe I should kind of dial back the zoom so we can see the whole thing. Are we doing okay so far? Okay. Well, if the condition of line 11 is false, where do we go?
13.
We go to line 13, and line 13 is asking, is A bracket M, which is the same as C bracket 1 at this point, is that less than K? No, that's not true, because K has a value of 5, and C bracket 1 has a value of 6. 6 is less than 5 is false. So where do we go next? We go to line 16. Okay. Line 16 does not even evaluate a condition because we don't have any choice left. We don't have to compare anymore. Line 11 checks whether they are the same. Line 13, see if the element is less than the value we're looking for. If these two are false, what does it imply on line 16? Has to be greater than. Okay. So on line 16, this is the fun part because we're going to invoke the subroutine again. Okay. And that means we have to set up the same columns, and this time we'll start it at this is hard to line up. Okay, so we have to start with that part here, and then we have to set up the whole thing again. What do we put on the return info? We are on line 16 right now. On line 16, the return info is just saying return whatever this invocation is returning. Because if you look at line 16, what does it do? It takes whatever the invocation is returning and return it as my own. Okay, in other words, this is what the subroutine is doing. It's like, okay, I'm supposed to search for a particular value in an array, with a deck of cards. Okay, I do my part. I pick out the middle card, compare, and go, okay, that's not the value I'm looking for, but I know which half of the array to toss away. Okay, I toss away the other half. Then what do? Well, I'm lazy, and I said, I've done something already. I don't want to do the rest. So what I do is I give the card to you. I give the stack of cards to you, and then I tell you, okay, you can search from here to here, and this is the value that I'm looking for. When you're done, let me know what is the result. So I just kind of go back and I sit around doing nothing. So you go ahead and do your search, right? What do you do? What do I do when you tell me, oh, the answer is no? I just pass it along. Oh, no, the answer is no because you told me the answer is no. And that's what this return statement is doing. It's just relaying the result back to the caller of B search. Are we doing okay so far with the concept of, what are we doing on that particular line, on line 16? Kind of?
It's just kind of a matter, if it's in your example, then wouldn't the second invoked, what do you call it, subroutine invoke another subroutine?
Is invoking the same subroutine, but it is a different invocation. So right now we are setting up the second invocation of bsearch. The first one came from line 20. That's our first invocation. Now we are on line 16. This is our second invocation of bsearch. It's not really different from the factorial example. It's just a little bit more complex. And this time we are passing a reference to an array instead of just passing values around. But have we changed anything about the treatment of a line that has an invocation to a subroutine that returns a value? Have we changed anything at all regarding that? Nope, we have not. Okay, so that's important. A is still a reference. Remember last time we talked about this. When you pass a parameter that is already passed by reference to you to someone who's also passing by reference, you just pass the reference itself along. Okay, you do not create an alias of an alias. Okay, what am I going to specify B? Well, this new B is the same as the old B, which is 0. And what do we specify? How do we specify E? E in this case is m minus 1. M is 1 already, so E becomes 0 for this invocation. K is the same because we're still looking for the value 5, so K is always the same. And M is a local variable. It always starts with an unknown value. And that's how we set up the columns for the second invocation of the subroutine. Now, at this point, it's really, really hard to keep track of everything, so I will do this trick here. First, I will shrink these columns just enough that we can still see everything. And then I'll pull this little tab here. It's not a tab, it's just a separator to this part. So now I can scroll this part of the screen independent to the rest. Okay. But I still want to see the values of the top, so I can split it again vertically like this. Yeah, but I have to do it because my screen size is really limited and I cannot use a small font size. When you guys do it, it's not nearly as bad because you can just pick a smaller font or zoom out a little bit, and you will still be able to fit the entire thing on your screen. Okay, so now what do? We are invoking the subroutine bsearch, so we better start from the beginning. Starting with line 7. Line 7 is checking B is greater than E. It is false because B is 0 and E is 0, so what B is greater than E is false. Then we go into line 10. Line 10 wants to compute the floor of B plus E divided by 2. This is easy, right? 0 plus 0 is 0. 0 divided by 2 is 0. And the floor of 0 is 0. So M ends up with a value of 0. Then we go to line 11. We perform a comparison. A bracket M equals K is false. Because M is 0 and A is a reference to column C to column E, so A bracket M is basically C bracket 0, which has a value of 2. 2 equals 5 is false. Then we go to line 13. Line 13 is checking, is A bracket M less than K? The answer is true. Because A bracket M is C bracket 0, which has a value of 2. K is 5. 2 is less than 5 is true. So in this case, we go to line 14. And what do you think line 14 does? Another invocation, right? Okay, but we are done. This is our last invocation. So we'll go ahead and set up, another bunch of columns. The return info of line 14 is we have to come back to line 14. The only thing left to do is to return whatever was returned to me. A is passed by reference. It is still a reference to column C to column E. In this case, what is going to specify B?
The former M, which is 0 plus 1, so
It'll be 1, right? Because because M is 0 already. M plus 1 is 1. And E is just whatever is passed to me, so it's a 0. And then K is still 5 because I'm still looking for the value of 5. M is a local variable. It starts with an unknown value. And that's what we are doing for this invocation. Are we doing okay so far? I know it looks really confusing because I have to split the screen into 4 parts and scroll, this portion here independently. Okay, so now we go back into the subroutine, B search, and start from the beginning again. Starting with line 7, but this time it's easy because B is greater than E is true. Woo. Yes. Okay. So what do we do when B is greater than E is true? According to this logic here, we just have to go to line 8. Okay, line 8 has one thing to do. It is returning the value of false. Now, what does return do again? When we execute a return statement, what does it do?
What's the
value.
Exactly, it replaces the question mark with whatever we are returning. What are we returning again?
False.
False. And so we just have to copy and paste the return info cell, change the question mark to a value of false. I just use F here to save some space, and that's it. Now, do we execute this statement right here?
No.
The answer is no. Okay, so even though it is another return statement, we just let it be. All we want to do is to replace the question mark with false, and that's the result of executing a return statement. We leave this statement alone. Okay, that is something that we do later on. Okay, that's very important because we have to make sure that we don't execute line 14 at this point. After line 8, where do we go according to this algorithm? We go all the way to line 19, which is the end of the subroutine. At the end of the subroutine, there are two things to do. The first thing is to look up return info and tells us, okay, we have to continue execution on line 14. And line 14 looks like this when we get back to line 14. Then we can say, okay, all of these columns are no longer of any use to me, so they are now all deallocated. Are we doing okay so far? So next, we go to line 14. And when we get back to line 14, we have to do about the same thing, because line 14 now looks like this. Line 14 is R19 at this point. So what we have to do is to look up its own return info cell. We have to scroll one more time. This is the return info cell that we have to use for line 14. And what are we returning again? Okay, we are executing this statement so that over here we replace the question mark with the value of false. Are we doing okay with this step? Okay, now I know this one is confusing because we are executing a return statement when the return info cell itself has a return. But that has nothing to do with anything, because all we are doing is just to replace the question mark. That's the result of executing the return statement. After we execute line 14, then we get to line 19. Line 19 is the end of the subroutine, so the first thing we want to do is to look up the return info cell. It tells us we have to go back to line 16, and when we do get back to line 16, this is what line 16 looks like now, because we have resolved what it is supposed to return. And then line 19, as the end of a subroutine, also has to deallocate these columns, so they are now gone. And now we continue execution on line 16. But remember, line 16 now looks like L21, the cell L21, so we are just returning false. We're executing return false. When we execute return false, what are we doing? We are looking up the return info cell, copy and paste it, and then change the question mark to false. That's the result of executing return false. After line 16, we also get out of the conditional statement, then we get out of the conditional statement, and we are now at the end of the subroutine. On line 19 again. On line 19, the first thing we want to do is to look up where am I supposed to go back to. Return info cell tells me I'm supposed to go back to line 20. And when we do get back to line 20, we are going to print the value false, but not right now. On line 19, the second thing we have to do is to clean up all the columns or deallocate the columns that were allocated to me. And now it's all done. I continue execution on line 20. And line 20 is going to print false to the screen. And we're all done. Yay! Yes, I'm pretty sure this time it is recorded, so that's good. Okay, let's zoom out. Okay, I have to do this because the algorithm itself is taking up a lot of space. So let's just kind of zoom out on the trace itself and see if we can fit the whole thing on the screen. Because I just want to give you, visually, how does the whole thing look like? Fits exactly, almost. Let me just zoom out a little bit more. There we go. Okay, I know people in the back may not be able to read everything, but that's what it looks like when you have something like this. Okay, so this is the first invocation. Now, if we just look at the invocation itself, all by itself is telling me what that invocation is about. This invocation is basically telling me that I have to search in the array, starting from column C to column E, but the index, the first index that may contain the value k, is 0. The index of the last element that can still have the value k is 2. 5 is what we are looking for. M is just a local variable. The second invocation is here. Now it is still the binary search algorithm, but the starting point and the ending points, one of them would have changed. In this case, the ending point has changed, which is basically saying we still believe that the element may still be in the array. The index of that first element that may have the value k is 0, but guess what? The index of the last element that can still have the value k is also 0. So we have shrunk the region of the array that can potentially have the value k in the second invocation. In the third invocation, which is over here, B and E have overlapped. B has gone past E, which is the indicator, and say, okay, there's nothing left in the array that can still have the value k. So the job of the third invocation is easy, because all it has to do is to go to line 4, which line is that? Line 8, and say, okay, I know for sure that the element is not in the array, because when I gave this problem to that person, there's no card left. So it's easy for you to tell me, I don't think the value of 5 is in this stack of card because the stack of card is empty. So I take your answer back and I say, oh, okay, well, the answer is no, it is false. I tell it back to whoever told me to search, with one card left, and then that person went back and say, okay, the answer is false to the person who wanted to find out whether the value is in the array or not. Okay, any questions about this trace?
Why would you do that? Why wouldn't you just do it yourself and get it done? Search the array.
Well, that would be the other algorithm, the iterative version of binary search, the one that we looked at before. That's doing everything myself. This one is basically delegating the job to somebody else. It's just that somebody else would solve a problem that I'm solving, except that problem is now getting smaller. And that's the recursion, or the ability to use recursion. Okay. Now in this case, which algorithm do you prefer? Do you prefer the original one that is iterative, or do you prefer this one which is recursive? Any preference?
I think the recursive is a little easier to understand.
It can go either way. Okay, it can go either way, but you can definitely see the relationship between those two. There are some algorithms where the recursive version is a whole lot easier to understand than the non-recursive one. And there are algorithms where it is exactly the opposite. You want to look at the iterative version instead of the recursive version. Okay? Yep.
Iterated is for a loop, right? And recursive is when the subroutine refers to itself.
Exactly. Exactly true. Okay. Now, without actually doing, the code, I want to show you something that you will see in some other classes. I'm just looking for a pen so I can draw something on the whiteboard. If I cannot find one, I cannot do it. Okay, I guess I cannot do it now. It's about, some other interesting data structures, like what is a binary tree, okay? Binary search trees. Related to binary search, but it's a tree instead of an array. I cannot do it here, so I will just kind of ignore that. We can just ignore that. Are there any questions about this particular algorithm? No questions? Yep.
What if it wasn't sorted, this wouldn't work?
If it is not sorted, binary search would not work. Binary search itself relies on an array being sorted first. That is true. Okay. Any other questions related to this algorithm? It's basically binary search that we have looked at, a few weeks ago, except it is now expressed as a recursive algorithm. Question?
Well, I was just thinking, in order to be able to use this, if it wasn't sorted, was there a way to sort the array so that you could use this?
Yep, there are ways to sort an array. There are a few sorting algorithms, but for a class like this, in terms of complexity, the easiest one to explain is what we call a selection sort. Okay, so we can take a look at the selection sort algorithm since you asked that question. So we'll go ahead and save this file first, and I'll call this recursive binary search. Okay. Can you remind me to talk about sorting next time?
Yes.
Because I want to show you, just another, subroutine, but this one does not have arrays and it's a whole lot easier. But it's still kind of fun because, it will do one thing that, defines, we'll just call this, let's give it a name. Okay, call it P. By val x, and then we'll say divided by 10 goes to x. This is our subroutine, and we're going to invoke the subroutine P with a particular value. Okay, we'll just pick one particular integer value. Let's say 56. We use 56 to specify x, and we want to find out what it does. This one does not have passing by reference. It does not have arrays. It only have passing subroutines, passing by value. Doesn't even need local variables. So we want to find out what this algorithm is going to do, and we have about 5 minutes. That should be enough time. This is one that is a little bit easier than the previous one. Okay, let's go ahead and find out what it does. We need one column for comment, one for line number. There are no global variables, so the precondition, there's nothing to say about the precondition. We invoke P first on line 10. We have to specify a return. Okay, this time should we have return line number or return value? Return line number, because we don't have any return statements. Okay, so it's just a return line number of post. And we have to pass a single parameter x. This time it is 56. Then we get into the subroutine starting on line 3. Is x less than 10? No, it is false. Okay. If it is false, we go to line 6. Line 6 is going to invoke the subroutine again. So once again, we specify the return line number to be this time line 7. And then we have to specify the parameter x. What is, okay, I forgot to do one thing here, which is to take the floor of that. Okay. So what is the floor of 56 divided by 10? 5, okay, that's easy. And here we go. We get back into the subroutine starting on line 3. On line 3, we are re-evaluating whether x is less than 10. This time it is true. Then we go to line 4. Line 4 is just printing the value of x, which is 5. And then we get out of the conditional statement. We get to line 9. Line 9 says we have to look up return line number, which means we have to go back to line 7 next, and then we deallocate these 2 columns. We get back on line 7. What does line 7 do? We're supposed to print x mod 10. What is x this time? X is 56, and 56 mod 10 is what? 6. The remainder of 56 divided by 10 is 6. That. Then we get out of the conditional statement. We go to line 9. Line 9 is going to remind us that we have to go to post next, and we deallocate one of these columns, and we are done. So if you look at what it's printing the number itself in base 10. If you change the 10 to 8, then we'll print the number out in base 8. If you change it to 7, it will print the number in base 7. Okay, so this is a printing program that can print a number in just about any base. Okay. So just a quick example, just to re-illustrate, the concepts of subroutines and passing by value and stuff like that. Question?
To make it easier to change what base you want, wouldn't you want to use
a parameter?
By val? Yeah.
Yep, you can use a by val as the base. Yep, that will make it easier. Yep. Very good. Okay, so I'll save the file and I'll see you guys on Thursday. Don't forget about the homework assignment. There's a homework to do on Thursday.
Just a quick question. When floor, if it comes out like 5.9, it will still be 5. How do you guess this? Like when you say floor 56 divided by 10, it comes out to 5.6, right?
Yeah, the floor of 5.6 is 5.
Okay, and then say if it comes out to 5.9, the floor is still 5.
5, that's correct. Yep, it's not rounding, it's always rounding down.
Okay.
Yep, it's the largest integer that is less than or equal to that number.
All right.
I just had a quick question.
Yep, go
I
ahead.
noticed you graded our last homework assignment.
Yes, I did.